the nuisance
yeah.
variables involved? Oh, what's going on there?
Seems like it started mid, like, presentation.
Is that? I don't know. It might be someone on Zoom. Sorry, were you talking to me there? Okay, that's fine. Okay. Okay, so observational studies with the study effect or non-randomized trials. Okay, so that's going to be a trial where there may be a lack of balance between potential confounders. Sorry, I'll just get you to turn your microphones off if that's okay. Okay. Okay, after we talk about these formal calculations, these are the Greek letter ones, I'm going to talk about informal approaches. And it's a bit of a funny thing. People seem resistant to informal approaches because they seem too simple. In other words, if I understand it, it can't be scientifically valid. It's a bit of a strange attitude. Mind you, they are very simple. They're very, very simple, but when there's a lot we don't know, it's probably a better approach. All sorts of stuff going on there. Everyone's having more fun than I am. Okay, the last thing, I've run out of time if I want to. I wonder if it's this horrible thing. It might be. Yeah. I will run out of time, so what I've done is I've just chucked a little bit on the end. I'm going to have to talk to Casey about making sure she's got a copy of these notes. I've also written these notes in a reference manual type of way, okay, so you can actually go through and find out the different formulas. Okay. Okay, so the first thing I want to talk about is study objective, and I should say design, okay? So the study objective and design are going to have a major impact on what analytical approach we use and the number of patients we're going to need. I don't want to go into too much detail about various study designs. There's lots of them. I want to split them into two main groups. First, experimental studies, such as randomized controlled trials. These studies tend to be meticulously designed and highly controlled. So the analytical approach we use in experimental studies is usually very, very simple, okay? And so it's a very simple approach and it lends itself to formal sample size calculation. Observational studies, on the other hand, often require complex multivariable modeling, and there are so many unknowns. It's such a complex system and complex model we need to use that any formal sample size calculation we use is meaningless because we have to make such large simplifying assumptions that it's just a silly exercise, okay? So in this case, we should probably use informal approaches. Now, one problem with this is not everybody seems to understand it. They seem to think that Greek letters mean good science, okay? And even if I have to be extremely simplistic, use a formula that is just silly, then that's preferable to using a formula where we're admitting we don't know, okay? So I guess we have to sort of unlearn some of our thinking when it comes to sample size calculation. And one of the problems is we have to deal with reviewers and we have to deal with assessors. And we don't really get, particularly with assessors these days, we don't get any rebuttal. We can't actually say, well, no, it would be inappropriate to do that for reasons X, Y, and Z. They just reject our grant application. That's it. We get no chance. So their misunderstanding of the problem will get our grant. So people just become practical and throw in Greek letter formulas anyway. Okay. So that's a very important aspect. The type of study design. The other thing I would like to talk about is the study objective itself. There are three main reasons we tend to do primary data studies. The first are exploratory studies. So we're trying to find, these are the what are studies. We're trying to identify potential risk protective factors out of a large set of predictors, okay? So in other words, what are the risk factors for type 2 diabetes. We could collect 20 or 30 exposures and see which ones are actually associated with type 2 diabetes. Okay? The second is predictive modeling. And here the focus is at the level of the individual patient, or I should really say participant. Okay? So we might want to see if we can diagnose patients or get a prognostic score for each patient or risk score a patient. So here the emphasis is on individual patients rather than making inferences about the population. In those two types of studies, the formal sample size calculations I'm using don't really work because they don't make sense. In other words, we're usually interested in a particular study effect when it comes to sample size calculation. So does a treatment work? Is a particular exposure important? Okay, it's not just, we've got a bunch of exposures, which ones are important? So that brings us to this third set of studies, okay? So answering a previously posed and very specific research question. So it includes most clinical trials, not all of them, there are weird clinical trials, but it includes most clinical trials and observational studies with a single study effect. Does BMI increase the risk of type 2 diabetes? I've mentioned BMI, a particular exposure, and that should be in the title of my paper or the title of my grant. It should be the primary research objective. So that BMI in that case is what we would call a study effect. It's not just one of many. Okay, so a large majority of sample size calculations for power are for hypothesis testing studies, okay? And what is power? Power is our ability to detect a true effect. That's what the power of a study is, okay? So if BMI is important, what's our chance of demonstrating that, okay? There are also sample size calculations called precision calculations, where power doesn't come into it, and that might be in predictive studies. So for example, we might want precision of sensitivity or precision of specificity or something like that, okay? And I'll come back to those right at the end. Okay, so really, just in this opening part of this talk, I really want to get this point across, okay? That sometimes it is appropriate to formally calculate a sample size, but very importantly, sometimes we shouldn't, okay? And really, if you do get an assessor or reviewer who does really understand sample size, they should rightly rip you to shreds if you use a Greek letter formula where you shouldn't. Okay, so really, there's three preconditions. This last one's a bit weird. I do want to talk about this, but there are three preconditions. The first is we can formally calculate sample size, one, when we have the information, the inputs to actually do so. Okay, so we need access to expertise, we need previous research and so on. So if we don't even know what the risk factors are, it's a totally new population, a totally new disease, or it just hasn't been studied very well, then where can we get this information from? Okay, that's the first one. The second one is the analysis should be sufficiently simple. Now, what that really means, the subtext here, is that the experimental design should be relatively simple. So it should be something like a randomized controlled trial where all of the confounders are balanced and we are just testing, does the treatment work? Okay? So can we actually answer our research question with a t-test? If we need to use multivariable modeling, maybe we shouldn't be considering formal sample size calculations. So if it's an observational study, that's much trickier. And third, and this is actually an ethical issue here, generally the study is prospective, okay? Now, I'm talking ethics when I say that. In other words, we don't want too many patients to be enrolled, or we don't want too few to be involved. However, and this is where this third one is a little bit wishy-washy, we also have resources as well. The cost of collecting data or the cost of processing data. So for example, I know MARTA has a very large routinely collected data set. Now, technically speaking, I should really just include all of that data into any study I do, providing it's of a certain quality. Okay, so I might actually have thousands of observations, but I may not need all of them from a power point of view. Should I put them in anyway? Yes, I should. Okay, even though my study is overpowered, because people should be able to spot overpowering of a study and take that into account when they read something. And I'll give you an example of this in a second. Okay, so I should use all of those thousands and thousands of patient records. The problem is the resources to actually clean all of that data. That's going to take someone who's a data manager. It might take them months and months of work. And I'm asking somebody for money to pay for that. So that's not really so much of an ethical issue. It's a resourcing issue. Okay, so we can also do sample size. So how few patients can I get away with? So we're thinking about it like that. So this third one, it's not a rule, but I guess we should call it a consideration. Okay, so I just want to clarify here. Why do we need sample size calculations? Well, because ethics committees and granting bodies want us to do them. Okay, now I'm not really being cynical there. There is a very good reason they want us to do them. Okay, I don't actually disagree with sample size calculation. It's a very, very good idea. I just disagree with them being done badly. Okay, so the main statistical part of this process involves selecting a method, so a t-test, a chi-square test, a linear mixed model, whatever, based on our primary endpoint, and then using the science. This is a calibration process, remember, using the science and a little bit of statistical theory to come up with a sample size. That, one, provides a reasonable guarantee that the study will reach its objectives. We can answer our research question. Okay, so it is sufficiently powered. It's powered enough. And two, to ensure that the study is not over-resourced, because if you're talking about H&MRC, that's taxpayer money, yada, yada, yada. Okay, so, and as I've said before, this is particularly important in prospective studies, in other words, where the data hasn't been collected yet, and that's very much around ethics, okay? I guess resourcing comes into it as well, but ethics is very, very important in a prospective study. The only real risk for retrospective cohort studies is patient identification. We're not going to hurt them. We're not sticking needles into people just for the point of doing research. Okay. Okay, so what if we get our sample size wrong? So I'm now going to talk about overpowering or underpowering. So first, overpowering. If our sample size is too large, we may see a statistically significant result. In other words, not due to chance or unlikely to be due to chance. That's the statistical side of it. But the effect may be clinically trivial. In other words, it doesn't really make any discernible difference to patients' lives. Okay, that's what will happen if we have too many observations. Something's significant, but it's not significant. Do you understand what I mean? The second is if the sample size is too small, the worst type of study, we may see something that is very, very important. The treatment may look like it does a great job, but we can't rule out this being due to just chance. In other words, in our sample, we see a huge treatment effect, but we cannot assume this is going to hold for the population from which that sample was drawn. Does that make sense? In other words, it worked in the sample, but we can't say it'll work in the population. Okay? And I just want to make a point here, and this is a pet, I want to say hate. I know it's a strong word. It's a pet hate of mine, and I get it all of the time in my papers, okay? I think it is silly to provide a sample size calculation in your paper, okay? In your paper. In your protocol, in your grant application, in other words, in your proposal, yes, that is the place for it, and we can trust our ethics committees to do the right thing. But all of the time, I get reviewer comments say, I want to see your sample size calculation, okay? Really, the reason I hate this and the reason I think it's unnecessary is we can use our eyes to see whether something is overpowered or underpowered just from the results of the analysis. We don't need to see a sample size calculation. I can spot it a mile away, and I'm going to see whether you can spot it too, okay? So I'm going to give you 3 examples here. We're going to work through them, okay? In the first one, so I want to know, is it appropriately powered? Is it overpowered, too many people, or underpowered? So the first one, all-cause mortality, that's my outcome, okay? A high-fat diet leads to a significantly increased risk of mortality. Those on a high-fat diet have 3 times the chance of death relative to those on a low-fat diet. Now, I have not told you the sample size here. My hazard ratio is 3. But I see that a hazard ratio of 1 is contained in that confidence interval, and it was not statistically significant. Now, does a hazard ratio of 3 sound clinically important to you? 3 times the chance of death. That sounds important. Can we say it holds for the population? No. We cannot rule out a hazard ratio of 1. So 3 is our sample estimate. It's not the true value necessarily in the population. So here is a case where we saw something clinically important, but we can't say that it holds for the population. Underpowered, overpowered, or just right? Which one? Sample size, okay. Sample size too small or sample size too large? Too small. Underpowered, okay? Okay, number 2, systolic blood pressure, just the continuous variable. SBP is significantly higher in men than in women. The mean difference was 23 units. The confidence interval was 7 to 39, and P was less than 0.05. Now, I'm assuming you understand your SBP here. Does 23 units sound like a reasonable amount? Yeah, it does. Okay, was it statistically significant? Yes. So just looking at that, would you say N was too large, N was too small, or N was about right? It was clinically significant, it was statistically significant. Okay, you don't need to see my sample size calculation. My study worked, okay? The third case, blood pressure control. So this is a yes, no type thing. Okay, so binary. The odds of blood pressure control is significantly higher in women relative to males. The odds ratio was 1.05. The confidence interval was 1.02 to 1.2, and P was less than 0.05. Is that a clinically important effect? No. No, I wouldn't think so. Well, yeah, you might say, but really, 5% increase in the odds, it's not really that large of an effect. Yet it was statistically significant. Here, our sample size was probably too large. In other words, a clinically trivial effect came out as statistically significant. So straight away, a reviewer should say, wait a sec, that's not important. Your sample size is too large, okay? So we really need to think carefully here and consider both statistical significance and clinical importance. Or we should really just say clinical significance and statistical significance. Okay, so where am I going to from here? I'm going to discuss these 2 distinct types of sample size calculation. The first being formal sample size calculations, in sufficiently simple analyses. And the second is the informal sample size calculations that we need to use in more complicated observational types of studies. So here is this message I want to say again. I shouldn't really say bivariate analyses because there are slightly more complicated methods that we can use and still do a sample size calculation, but the principle holds, okay? That generally only analyses that can be adequately analysed. I can run a t-test on anything. That doesn't mean it's right to run a t-test on anything. Okay, so adequately analysed using a bivariate analysis lend themselves to formal sample size calculation. For analyses requiring multivariable modelling, okay, so large observational studies without specific study effects, we should really use informal approaches. Okay, the good news is that fortunately most situations, even those that are a little bit complicated, do simplify down to much simpler problems. So now what we'll do is we'll cover the basic sample size calculations. And then I'll go on to show how these can be extended a little bit for various situations. Okay, and again, I just want to remind you, I haven't covered everything I'm not going to talk about everything because I know I'll run out of time. So I have left a couple of formulas at the end. And if we do have time, anyone want to ask questions about, that's fine. Okay, but I do want to remind you that no matter how horrible these formulas get, please remember, formal sample size calculations for power are about ensuring statistical significance aligns with clinically meaningful effects. It's for calibration of our statistical analysis to scientific reality, okay? That's your one take-home message from this. The rest you can forget about and then just come back to the lecture notes when you need to calculate it, okay? Sample size calculation is about aligning statistics and science together. All right, I should say statistical tests and science together. Okay, so I know you've been waiting very patiently to see these Greek letter formulas, and I know you can't wait, you're getting very excited about them. So let's start our first one, our first formal sample size calculation. I'm going to give you an example. We want to investigate the efficacy of a new therapy to reduce back pain. We'll use a randomized control trial with two arms, in other words, your standard setup, a control arm, which is a placebo or a usual care type arm, and then some sort of brand new wonder intervention, okay, that we are trialing, that we want to see whether it provides superior patient outcomes, okay. Our outcome in this situation is a validated instrument for measuring back pain. It's on a scale of 1 to 30. We can more or less treat it as continuous, okay? So just to clarify, this is a standard two-arm parallel RCT with a continuous outcome measured once after the treatment effect, okay? It's measured at baseline as well, just to check that everything's balanced, but we're not bringing that data into the formal analysis, okay? It's only after the treatment has had time to work that we want to compare people. It's an independent t-test problem, in other words. Okay, so let me start. There are 4 ingredients, and I think the thing we need to remember about sample size calculation is it is like baking a cake. You need your ingredients, you mix them together, that's it, okay? And it is arithmetic. It really is a very simple thing to do. I will talk about software that people can use towards the end, but I really want us to get our hands dirty with the calculations. Okay, so there are 4 ingredients that we need in this situation, and actually in most situations. These 4 ingredients you will see in all formal sample size calculations. It doesn't change. The nature of them change a little bit, but what they are. The first is significance level. That is setting where we would reject the null hypothesis. P is less than 0.05. You don't even have to think about it. almost always, not always, but almost always, we will use 0.05, okay? What that means is there's less than a 5% chance we will say the treatment works when it really doesn't, okay? We call that failure to do that. Saying a treatment works when it really doesn't is called a type 1 error. And that's supposed to be the bad one, but it actually does change depending on the study. Okay, so that's significance level. Number 2, beta, which is related to the power of the study. How sure do we want to be that we can detect a difference or an association that is truly there? Okay, so note here that power equals 1 minus beta, where beta is the probability of a type 2 error. Type 2 error is failing to recognize that a treatment works when it really does, okay? So our power, just to turn that around, our power is our ability to detect a treatment that works, all right? And we generally set that at 90% or 80%. What that means is 9 times out of 10, we will detect a treatment that works when it really does, or 8 times out of 10, we will detect a treatment that works when it really does. Okay, those two are very set. So here, significance level 0.05, 5% chance of a type 1 error. Beta is almost always 90%. Then we find out that's got too many patients, so then we go to 80%, almost always. But it's 90% or 80%, okay? It's very hard to justify varying power from either of those two numbers. Now we get to a very, very important one. And why I think this is important in particular is people get this one wrong all of the time, okay? Delta MCD is the minimal clinical difference, okay? Now, I really want you to remember that name, minimal clinical difference. What's the smallest amount that would represent a scientifically meaningful difference or an important difference? Okay, it's often represented in books by mu1 minus mu2, which totally confuses people because they think that means x bar 1 minus x bar 2. So I would really stay away from that way of representing it. Okay? Now, the point is, and this is where people get this wrong, is where should this number come from? I'm just interested to hear your views. Where should we get that number? That's right. Where shouldn't we get the number? The results section of previous papers. Okay? Now, what I see is people saying, I don't know what that number is. I'm not going to back myself. Okay, so I'm just going to get it where it's written down somewhere else, even though it's a totally wrong number to use. Okay, so it's from expert consensus usually. Okay, I'll come back to that one. And the reason I'm sorry, I feel like a school principal here, but the reason I'm saying this is so many people get this wrong. They just go to the results section of previous paper. That is an observed difference. It may or may not be clinically important. Okay, the fourth is the standard deviation. How much variation we would expect within a particular group. So whether it be the control group or the treatment group. Okay, if the standard deviation is high, we're going to need a larger sample. So if we have these 4 ingredients, we combine them together and we calculate our sample size. So here's our first Greek letter formula. And I'm going to give you 2. I'm going to give you the case for 2 independent samples. I should really say that's a number of patients here. And I'm also going to give you it for the paired sample case. So the before-after type study where it's the same patient. Okay? But we're not even really going to talk about the paired case. I'm just going to concentrate on 2 independent samples. So there's no relationship between the people in the 2 samples. They are independent of each other. Okay? Just out of interest, but if we do look at that formula straight away, we can see that the paired formula is more efficient. It only, all else being equal, it only requires half the number of patients. That's because any difference must be due to the treatment, okay? It's the same person, okay? So any difference must be due to the person. Whereas in 2 independent samples, there's also the natural variation in people that we throw in with the treatment effect. All right. And by the way, this higher efficiency of paired samples is nowhere better displayed than in crossover designs. All else being equal, crossover designs need about 1/6 of the number of patients that an independent sample needs. The only problem with crossover designs is they only work in very specific situations. Okay, an alternative representation of this, it's really exactly the same formula, is I bring this standard deviation down to the bottom, which is fine, and represent it like that. The reason I'm showing you this form is that this quantity here, this delta MCD over standard deviation, is often called effect size or Cohen's D, or sometimes Cohen's delta, okay? And it represents how many standard deviations apart the 2 groups are. So it's actually a way of, when we don't know anything about our data, we can just say, we want to find a moderate effect size, and we can just put a number straight in there and say, well, we want them to be half a standard deviation apart. We often use it when we don't know a lot about our data. Okay. We'll also see this specification when it comes to the longitudinal studies. Okay, so that's enough talking about the formula. Let's actually do it. The last thing I need to talk about is what are these Zs about? Okay, there they are there, Z and Z. They are bringing in normal theory, okay? The statistical theory that I was talking about before. So they are a way of bringing our significance level and our power level into the calculation. The good news is that there's actually only 4 numbers. It's really just quantiles from the standard normal distribution, and there's an infinite number of them, okay? But there's only about 4 you will ever need, and 2 of those are much more common. This one you will use all the time. That's where that 2 standard deviations from the mean rule comes from. Okay, it's actually not 2, it's 1.96. Okay, so for Z1 minus alpha over 2, we almost always use 1.96. If we want 90% power, we would use 1.28. If we want 80% power, we'd use 0.84. Okay, so really those 3 numbers are the ones you'll generally use. Sometimes if we only do a one-tailed test, we may use this number here too, okay? But generally, it's those 4 numbers are all you're ever gonna need. Okay, so let's now do the calculation. We want our 4 ingredients, and the real trick to sample size calculation is set out your ingredients first on a page, then mix them, okay? Throw them into the formula. It is arithmetic, and you can calculate it. Okay, so the error rates, the no-brainers, we don't have to think about them at all. Alpha is 0.05. It is a 2-tailed test, so I've got to divide that 0.05 by 2, and I use 1.96 from right there, okay? 1.96, there it is. If I want 90% power, so in other words, beta equals 0.1, I will go and use this number here. If I wanted 80% power, I would have used that number. Okay, so I don't really have to think too hard about them, okay? Here's the trickier ones now, okay? Now, again, this is for clinical experts. It's not from previous papers, okay? We believe, as clinical experts, that a therapy that could not reduce back pain by 3 units on our back pain scale is not worth it. okay? It's just not worth it at all. It would cost too much, or it's unethical or invasive, whatever reasons, it's just not good enough to adopt it, okay? So in other words, it needs to be at least 3 units lower. Back pain needs to be at least 3 units lower. 3 or more. If it's not, it should come out as not statistically significant. Again, remember, calibration. Okay, and this must be based on clinical expertise. And here, I'm sorry, and I just want to say it because I just see people make this mistake all the time. It must not come from the results section of a previous study. It can come from the method section of a previous study. We consulted a panel of experts and they said that our MCD should be 5 units. That's fine. You can cite that paper. That's great, but not from the results sections. Okay, great. And number 4, a pilot study. We collected 10 patients. We just sort of trialed it. It might have been a phase 2 type of study. A pilot study suggested that the standard deviation in back pain we can expect within a single group, say just a control group, is about 6 units, okay? So we can get that from previous research, we can get it from a pilot study. We should, if we use previous research, we should assume that 1, it's the same instrument that they used, and 2, that the population is not too different. Or they might be very different people, but the measure itself should be similar. It doesn't matter if it's a different country, as long as they experience pain in much the same way, okay? So now we have our 4 ingredients, we can bake our cake. And here it is. Ugly formula gets converted into simple arithmetic, okay? There it is right there. And we find that we need 83.98, which we round up. We always round up. It could have been 83.0000001 and I still would have rounded it up, okay? So we round up to 84 individuals per group. So our sample size that we require is 2 times 84, which is 168 patients, okay? Did we follow that? Okay. You might ask, why couldn't I just have used pass and avoided all of that horrible stuff? Because understanding what we're actually doing is important. Once you understand the formulas, it's fine to use the software, but you shouldn't use the software if you don't understand the importance of the ingredients. Okay, I shouldn't say the formula, I should say the ingredients. They're very important that we understand what they're for. Whether you understand the formula or not is really sort of irrelevant. Okay, so now let's consider a formal sample size calculation for a binary outcome. And the one thing I would say is, all else being equal, binary outcomes require larger sample sizes than continuous outcomes, because continuous outcomes give us more information, okay? Okay, so if we have a cross-sectional study, like 1 time point or an RCT with a single follow-up, regardless of the method we use, logistic regression, chi-square test of independence, we can calculate the sample size we need based on a test of difference between proportions, okay? So let's consider example, a national study of type 2 diabetes patients. Diabetes is my favorite disease, I always talk about it. From 600 hospitals across Thailand. This is actually a real study. Our research question is there a benefit to specialised diabetes clinics? Okay, so these are clinics that had specialists in them. They were resourced in a slightly different way, tailored specifically for people with diabetes. Okay, and are these clinics better than general medical outpatient clinics in terms of patients achieving clinical targets, okay? So we were going to assume that a pilot study has been conducted, but the main study has not been done. So in other words, we need to prospectively power this study. And by the way, yes, we're going to use 600 hospitals. It's a huge study, okay? We will assume that the study is to be an RCT. Patients will be randomly allocated to either general medical clinics or specialized diabetes clinics. Why is this important, that patients be randomized? I just want to check you've been listening.
Generalisation of the population.
We do get the generalised, I don't mean a random sample of the population, I mean randomised to the two arms. What it really means by randomisation, it means that both groups are exactly the same except for the type of clinic. In other words, if there's any differences between those groups, it must be due to the clinic. Okay, and that's why RCTs are so wonderful and people love them, because they're very strong evidence, okay? As opposed to an observational study where, for example, we might say public hospitals and private hospitals. Well, private hospitals, people are richer, more affluent, whatever. So is it the private hospital or is it the fact that they're all rich that is responsible for the differences? So there's confounding and all sorts of issues like that, okay? But the other issue of why it's important is because if it's an RCT, we can use a simple analysis, a bivariate analysis to actually conduct it. If it's multivariable, these sample size calculations won't work because they're an oversimplification of the problem. Okay, so our research question is there a difference in the proportion of patients, or we could say prevalence, of patients achieving the diabetes clinical targets between those attending general medical and specialised diabetes clinics? Wow, I'd better move along actually. So very, very, very quickly, what do these clinical targets? We've got blood sugar control, we've got blood pressure control, we've got cholesterol or low density cholesterol control. So basically it's only patients that controlled all three of these who achieved our clinical target that we're interested in. So all ABC, by the way, these are called A, B and C for HbA1c, blood pressure for B, C for cholesterol. All ABC will be 1 if patients achieve the clinical target, all three, and 0 where they did not achieve all three. Okay, so here it is right here. Okay, we have an outcome, all ABC. We have a study effect, a particular X variable of interest. Okay, so our study effect is our patient department type, specialised diabetes or general medical clinic. Again, this is a 2-arm parallel RCT. The difference this time is we have a binary outcome, not a continuous one. Okay, so again, going to our 4 ingredients, okay? They are exactly the same 4 ingredients, it's just how we specify, particularly down here, is a little bit different. Again, alpha, 0.05, beta, power, 90%. We're going to use the no-brainers. And then we come to our minimal clinical difference. Now, a pilot study revealed that general medical clinics, our baseline value in other words, general medical clinics have about a 7.5% achievement of ABC rate. In other words, 7.5% of patients achieve all 3 clinical targets, okay? And we believe expert consensus, now this would probably be done on health economics, okay? Is it worth it? Okay, so expert consensus, whether it be health economists or whatever, any improvement that is not more than 2.5%, so from 7.5% to 10% is not worth it. Now 2.5% doesn't sound like a lot until you start thinking about health economics. If you achieve these clinical targets, you go a lot longer without getting complications. That saves, well, the country a lot of money, but it also, these people live a lot longer and so on. So 2.5 doesn't sound like much, but at a national burden of disease level, it's actually a huge amount. Okay, so here we also need we can actually calculate the standard deviation based off these 2 values. It's actually a very simple calculation, and this is what makes it different from the t-test situation, okay? That we can just calculate the variance, well, standard deviation or variance of our estimate right there. Sorry, I shouldn't say estimate of the data. Okay, so here we are, 4 ingredients again. We have alpha is 0.05, power is 0.9. Our MCD is 2.5%. And our variance is actually 0.1594. Now, you might say, wait a sec, weren't we calculating the standard deviation for the t-test problem, for the continuous variable? The answer is yes. But since this formula here is already squared, the variance is the standard deviation squared, if I calculated the standard deviation, I would just have to take the square root of that and then just square it again when I got to the formula. So I'm not going to bother, okay? You can calculate the standard deviation if you like, but I'm not really going to bother doing that. So you'll see in the formula, see it's squared anyway. So I'm not actually going to bother taking the square root to get the standard deviation, just to square it again to get back to the variance, okay? So here is our sample size formula for our test of proportions, our 2 proportions, a binary outcome, 2 groups. There it is. To spell it out in full, there it is there. And it looks exactly the same as the paired t-test formula. It is exactly the same, except how we calculate these values are a little bit different. Okay, so plugging it all in, we had 0.05, that's our Z, 0.975. We had 90% power, those are our no-brainers. We had the variance, and we had the MCD. Our 4 ingredients mixed together will give us a sample size of 2,678 individuals. We have 2 groups, that's going to give us 5,356 individuals. Now, there's 2 reasons that sample size is so large. One, it's a binary outcome, and binary outcomes require bigger sample sizes. The second reason it's large is because our effect size is quite small. It's only 2.5%. Had it have been 5%, not 2.5%, it would have actually been a much lower sample size. So the smaller our effect size, the larger the sample size. Okay, so we're going to round this up to 5,400 individuals. And how are we going to do this? We're actually going to sample 200 patients from 27 hospitals across Thailand. We're going to get, at each hospital, we're going to get 100 patients from the general medical clinic and 100 patients from the specialised diabetes clinics at each hospital, okay? Now, I want you to notice this for later, because this is actually an example of a multi-centre trial. There's something else we need to worry about. Okay, so many health outcomes that we often observe have what's called a clustering effect. Now, what is a clustering effect? What it is patients attending the same clinic and seeing the same doctors may be treated more similarly than patients that attend different clinics. And what we see is a clustering of results. What it really means is patients within clinics, in terms of our outcome, patients within clinics seem more similar in their value than patients that attend different clinics. In other words, if we looked at it on a graph, patients attending the same clinic would cluster together into little groups. Okay, and that's why we call it a clustering effect. So what this really means is patients that are in close proximity, they attend the same clinic, have this clustering together. They're what's called correlated. Okay, so the patients, not the variables, the patients are correlated. And this is called a clustering effect because we see clustering. And what it's got to do with is our study design. It's an artifact of our study design. Okay, because we have 27 hospitals, each with 200 patients, those patients in each of the hospitals will cluster together. We need to account for that. If we don't, we're going to underpower our study. The statistical implication of this is the standard deviations within groups will be underestimated, leading to artificially narrower confidence intervals, which lead to increased type 1 error. In other words, we're going to say the treatment works more often than we should if we don't account for this clustering effect. Okay? We also need to account for this in our sample size calculation. Okay, and things do get, we're moving away from vanilla formulas here, and we're adapting these formulas for our study design. So there are a number of ways we can actually adjust for this clustering effect, this design effect. The simplest way is to apply a sample size inflation factor based on the degree of clustering, how similar patients are that attend the same clinic relative to patients that attend different clinics. Ideally, we can find this from previous research, and let me tell you, almost no one reports this number, okay? So no, in practice, we can't get it from previous research. It's quite rare. So instead, what we do is we guesstimate it. And the general guidelines that are used is, oh, by the way, I should mention, how do we quantify this within group clustering? We use what's called an ICC, which is the intra-class correlation coefficient, or we could call it the intra-cluster correlation coefficient, or intra-hospital correlation coefficient. But typically speaking, is ICC of 0.01 is considered a weak clustering effect, 0.03 a moderate, and 0.05 a strong. And I think generally, which one would I choose? I would think about the variable itself, okay? If patients in Australia are treated exactly the same, and it's not a psychosocial element to the outcome itself, then clustering should be weak. But if patients talking to each other or being treated by the same doctor might influence the value itself, we would go towards the stronger end, okay? Whether you achieve HbA1c control, blood pressure control, and cholesterol control, it shouldn't really be highly clustered. You do or you don't, okay? I think how it's measured is routine blood work. I don't think it's got to do with treating doctors, and I don't think it's got to do with talking to other patients, not psychosocial at all. So if I was going to estimate this, I would probably go with a weak clustering effect, and in my grant application, I would say that this is not psychosocial, and it's a routine blood work measurement. In other words, different hospitals are going to measure it different ways, okay? So what do I do? Let's assume it wasn't in a previous paper, which, by the way, I've looked for this, it's not. Now we can calculate what's called a sample size inflation factor. Here it is. So our inflation factor is 1 plus the cluster size, and we said 200 patients per hospital, and the ICC. So in our case, we had 200 patients from 27 hospitals, and our calculation is this, 2.99. Now, what does this mean? I have to triple my sample size. So I multiply my original sample size by 2.99. This is the sample size inflation factor. This very weak clustering means I have to triple my sample size. So I'm going from 5,400 patients to 16,146. From a very weak clustering effect, okay? Clustering is an evil, evil thing when it comes to conducting research, okay? Now, I just want you to note a couple of things here. First of all, sample size inflation depends on the size of the clusters themselves, but is independent of the number of clusters. That's not strictly true. It comes out in the wash. But the take-home message here is lots of small clusters are better than a few large ones. In other words, I would be much better off going to 400 hospitals with a lot fewer patients than 27 hospitals with 200. Now, by the way, I should point out biostatisticians are rich and unethical, okay? We don't think about how much it's going to cost you, and we don't think about the poor patient suffering. We just say, this is the best scientific quality you can get. We do actually think about it, but we will say this is the best scientific quality, And then in reality, we have to go back and forwards, okay? So lots of small hospitals or big hospitals but only a small number of patients is going to be much better. Now that's not practical at all. It's not practical. Okay. The other thing to note that even a small design effect, 0.01, can have a profound impact on the sample size. We tripled our sample size even with a very weak clustering effect. The third thing is we've actually only dealt with this on the design side. You also have to model the data in a particular way when you have these sorts of design effects, okay? So in other words, your statistical analysis section will have to have special models for this. Mixed models or generalized estimating equations are the way we tend to do this. Okay, so the key point, all else being equal, many small clusters requires smaller sample size than fewer. The ideal cluster size is 1, okay? 1 person from each hospital, which would give us an inflation factor of 1, okay? If you look at the formula. 1 minus 1 is 0, so inflation factor is just 1. In other words, an independent study, okay? Or a single centre trial is the other word for it. The other point is regardless of whether patients in both arms occur at a single centre or not, as in a cluster randomised trial where we randomise the hospitals to the treatments, okay, such as step wedge and things like that, it doesn't actually matter to the sample size calculation. So whether people in each hospital are receiving both treatments or that the treatment is associated with a hospital itself, the sample size calculation is the same. Okay, so just one other point I do want to quickly make about this is sometimes we know the number of patients or have an idea about the availability of the number of patients, but we don't know the number of clusters, the number of centres we should get. So what we can do is actually work it out like this, okay? It's a very similar formula. We are just throwing this M down the bottom of the formula, and you'll see that the inflation factor has just been worked directly into the original formula itself. I'm not sure how good your maths is, whether you can spot that, but that formula is pretty much exactly the same, except for the inflation factor itself, and I've also put M here because it is the number of clusters, not the number of patients. Okay? And just note that this formula is for the binary outcome. Had it have been for a continuous outcome, it would look exactly the same, except I would have a 2 out the front here. Okay? Cool. Okay, now let's go on to longitudinal studies. The thing is I've already done the hard work here. There's a longitudinal study is just really, it's like a multi-centre study, but the person, the patient is the centre. In other words, repeated values from me, I'm like a hospital, okay? So I have individual observations, that's one cluster. You have individual observations, you're another cluster, and so on. The formula is exactly the same. All I've really done here is replaced M with T, where T is the number of observations per patient. It's the same formula, okay? Here, again, I've really just represented the ICC by row, but again, it's exactly the same formula, okay? So really, I'm just saying, how good is your maths? You will recognise that formula and that formula are equivalent. The only difference is M is the number of patients per cluster and T is the number of observations per patient, because patient is the clustering effect in a longitudinal study. Okay, so let's do a very quick example using longitudinal data. Outcome is quality of life, measured using a functional assessment of patients undergoing cancer therapy. That's a mouthful. So the FACT G instrument. Is a new chemotherapy regimen successful in reducing side effects? And we're also going to run this alongside a non-inferiority trial, which I'm not going to talk about the sample size calculations for that. Okay. We have the usual items, our 4 items we know and we love. Okay, so we've got our 0.05 significance level, we've got 90% power. We have a standard deviation within group from a pilot of 10 units on the FACT G instrument. And we believe, based on our panel of clinical experts, that if you cannot increase the quality of life of these cancer patients by at least 5 units, then it's not worth it. Okay? Now, here are some extra items. This one's very simple. How many time points do we have for the patients? We are going to get a baseline value, a first follow-up, and a second follow-up from each patient, so T equals 3. And we don't know what the clustering effect will be, so we're going to assume that the ICC is 0.6. Now, I should point out here, I think I pointed out later. No, I'm not sure if I do. I should point out that the ICC is much higher in repeated measures studies, because it's the same person, than it is in cluster designs, where it's different patients but then within the same centre. Okay, so we wouldn't use an ICC of 0.01 here. Okay, basically the way to think about it is how correlated is my baseline and last observation. If it's lots of parallel lines, they're highly correlated. So if people represent parallel lines on the graph, they're highly correlated. If they cross over like that, it's less correlated. Okay, sorry, I've sort of had to cover that very quick. Okay, so here it is. Again, it looks like an ugly formula, but I'm just plugging in values and I have arithmetic. There's my significance, there's my power, there's my 3, can't say follow-up, my baseline and 2 follow-ups, so there's 3 observations. There's my ICC of 0.6, and I'm plugging it in, and I find that I need 62 patients per arm, so 124 patients all up. If I assume a dropout rate, which is always going to be a consideration in a longitudinal study, of 10%, I can actually just plug that into a formula like this. So my new sample size is the old sample size over the proportion of patients retained. Okay, so in other words, my sample size is 138 patients, not observations, patients. Okay, so, oh God, I've got that wrong. I've said there's 5 observations, there should only be 3. Ish. Okay, sorry about that. We've got 138 patients times 3 is 390, 404, something like that. Anyway, you get what I mean. So sorry about that. That shouldn't be 5, it should be 3. Okay, I'll fix those up, fix that up. Okay, so I just got to watch the time. I only got 15 more minutes. So the sample size calculations we've covered so far have been strictly for quite controlled studies. Okay, that is when a bivariate analysis is sufficient or something not too much worse than a bivariate analysis. A longitudinal study like the last one, that's not bivariate. But there's only 2 variables. There's treatment and time in the model. Okay, so it's strictly speaking not bivariate, but it's still tightly controlled. We don't have to worry about confounding and things like that. These formulas are not appropriate when we have several predictors and we need to conduct some sort of complex multivariable modeling. In this case, we have 2 options if we're doing multivariable modeling: variation to the formal calculations. Now, I would only do that if it is a study with a study effect. That is a particular X variable of interest. So not an exploratory study, not a predictive study, but something like a non-randomized trial or an observational study with a particular study effect. For example, is BMI a risk factor for diabetes? I've mentioned BMI in my research question. That's fine. Okay. The second is the informal sample size calculations, which I'd use in exploratory studies. So if I don't have a particular study effect, I'd go with informal. But selling that is a different matter. So I'm going to just cover the first of these approaches, which again is just an extension to a basic sample size calculation. Here, I would use this for a non-randomized trial or an observational study like a cohort study with a single effect of interest, a study effect. Okay, so here only a single predictor. What we would do here is you can see that formula, it looks exactly the same. We've just added this one extra term here where this R squared represents the multiple correlation coefficient of Y with the other X's. So with the covariates, not with the study effect. So for example, if BMI was my effect of interest, but I also want to account for gender, age, and smoking status, then it would be the correlation of, what was my Y again? Let's just say blood sugar control. It'd be the correlation of blood sugar control with gender, with age, with smoking status, not with BMI, okay? And a multiple correlation coefficient we can just see as the average correlation of those three things. You could probably use that as a surrogate if you liked. Okay, you can actually calculate multiple correlation coefficients, but we need data to correlate coefficients. So a guesstimate is often what we would use there. Okay, so what we're doing here is we're just going to inflate our sample size due to nuisance covariates in our analysis. Okay, and again, don't use this with exploratory or predictive studies. Okay, only non-randomized trials and observational studies with a single effect. I'm not even going to run through an example of this. Okay, so again, just a few things that we should note about the situations above. All of these studies were prospective. So as such, there were feasibility and ethical issues that will limit how many patients we can collect. And most importantly, our research question can be adequately analysed using simple tools, simple methods and models, okay? What do we do when we have exploratory studies? That's where things get a little bit tricky. The good news is that it's actually very simple. It's much simpler to do an informal sample size calculation than it is to do a formal. So let's look at an example here. We have a retrospective cohort, so the data's already in hand. A retrospective cohort of type 2 diabetes patients. We want to know what are the important determinants or risk factors or exposures, whatever you want to call them, determinants of cholesterol control in diabetes patients. In this, so I want to know, is this study 1, hypothesis testing, 2, exploratory, 3, predictive? Which of those 3 is it? Here's my hint. What are the risk factors? That's right, exploratory. Okay, it's an exploratory study. I'm not mentioning a particular effect, and I'm not focusing at the patient level like in a predictive model. So it's exploratory. I want to know what are the important factors for a patient when it comes to their LDL-C control. Okay, so our outcome is cholesterol control, whether they can keep it under 100 milligrams per deciliter. And I have, in this case, a relatively simple situation where I have 1, 2, 3, 4, 5 covariates that I am exploring, okay? Now, a question here is we've got 5 predictors, but how many parameters are we going to use in the model? Something you may not have actually ever thought about before. Okay, so we're going to use a rule called the 10 EPV rule, which is 10 events or 10 cases per variable. Now, that's a misleading name because the problem is people will actually use the outcome as a variable. We're not using the outcome as a variable, so I actually prefer the name 10 cases or 10 events per covariate rule, so per X variable, okay? So which is the better approach here? And I want you to really think about this for a minute, okay? 1, should we admit that we have limited knowledge of this complex system and use an informal approach to calculate sample size? That's one option. The second option is, should we use a formal sample size calculation and force inappropriate guesses into this formal sample size formula, which is representing an obvious oversimplification, which is also probably incorrect, of our study design. Which is the better option? Admitting we don't know and using a simple formula, or pretending we know and putting some Greek letters on the page?
First option.
The first option is idealistically correct. The second option is probably more cynically correct, okay? And that's a horrible thing I have to actually say, but so many people I have seen will know that it's an inappropriate thing, but they just make sure there's lots of Greek letters and people go, oh, Greek letters, good science, let's let it through. Okay, I've seen that a lot. Not so much if you're talking about NH and MRC, but I've seen it slip through some ethics committees in my time, okay? So just, I want you to remember this, and whichever method you use, and I'm not going to actually judge you and tell you to use one method or the other, but just I want you to at least know that Greek letters do not necessarily imply good science, okay? Just because you don't understand something doesn't mean it's actually good science. And actually the reverse is true too. I have heard people say, that's too simple. That's too simple. How can that possibly be right? I understand it. Okay, so what did I mean before when I said the number of parameters rather than the number of covariates? We have to admit how many parameters each variable will include in a model. Now remember, when it's groups, we're comparing mean differences. When it's a continuous variable, it's just a straight beta in our model. So hypertension has two levels. So it's 2 minus 1. It's going to have one parameter, which is how different are people with hypertension relative to those who don't have hypertension. Okay, age is continuous, it has one parameter. Gender is one parameter, which is the difference between males and females. BMI is 3 parameters, so compared to healthy, underweight effect, overweight effect, obese effect, okay? Now that's weird. Sorry, I mean, I've sort of really had to skirt around this, but this is the number of things that a model will estimate. We don't actually estimate the 4 groups. We estimate 3 parameters. The difference from normal weight or normal BMI, okay? I've had to sort of skirt this. So duration, basically just remember, it's a degrees of freedom thing. Number of groups minus 1 is always used. Okay, so the duration of diabetes, which is continuous, is 1 parameter. So we have 1 plus 1 plus 1 plus 3 plus 1 equals 7 model parameters. Now, let's look at our magic formula, and it is so simple, this formula. Okay, we have 7 model parameters. Now remember, we want 10 cases per parameter. So using our 10 EPV rule, we want 10 cases or 10 events times 7 parameters. We need 70 events in our data set. Now, previous research has revealed that 1 out of every 3 patients achieves cholesterol control. So in other words, it's got a prevalence of about 33%. Now, if only 1 out of every 3 patients controls their cholesterol and we have 70 people controlled, that means we need another 140 who aren't controlled. Okay, does that make sense? Because we need 70 cases. To get 70 cases, we need 210 patients because only a third of them will be a case. Okay, it really is as simple as that. So 1 over the prevalence times the number of cases. And we work out the number of cases because we need 10 cases per parameter, okay? Some people would just multiply it by 5 because we've got 5 variables, but strictly speaking, it should be by 7. Okay. The other important thing to note about this is the lower the prevalence, the higher the sample size. So for example, if only 5% of patients achieved cholesterol control, in order to get 70 cases, we're going to need 1,400 patients, okay? And by the way, that's also true in the formal sample size calculations too. It comes through in it. The rarer an event is, the more patients we need. Okay, sorry, I've only got 2 more minutes. Okay, very, very quickly, I will also talk about another approach when we're doing exploratory studies. And this is not one that I necessarily suggest you do. It's very good. It's very convincing, particularly if you're considering an NIH and MRC grant, but it takes a lot of time and effort. Okay, so simulation of sample size is a very involved process, and I'm not going to go into how it works. But it's probably a little bit more convincing than this approach, not because it's scientifically better, but just because it actually appears much more involved. In fact, technically, this rule was worked out based on simulation. Okay, so here we guess what our model's going to look like. Our final model's going to look like. We specify some parameter values and then do it. We actually do an analysis 150,000 times or something like that, and actually come out with what are called power curves. And I'll show you that in a minute. So we're using Monte Carlo simulation methods to run 150,000 fictitious analyses and then seeing what the power was for different sample sizes. So here we go. Here's one I actually did. We ran this on 150,000 simulations based on a model with 6 predictors. Of these, only 2 covariates interested us. So we had 2 study effects here. So we had a treatment, and by the way, I've changed the names of the innocent here. We had a treatment effect, we had a genotype effect, and its interaction. Those were our hypotheses about those 2 main effects and their interaction. And I'm not really interested in the other 4 covariates, but they were real things. We just didn't want to test hypotheses about them. So here we can see for both the main effects, treatment and genotype, that 600 patients here, that 600 patients or so, maybe a fewer, would get us 80% power, okay? For the interaction effect, we'd probably want 800 because a lot of the time people will just use p equals 0.1 for to power interaction effects. But the point is in this type of study, we probably could have got away with 550 to 600 patients, okay? So we would include that graph in our grant application and say, we want 600 patients. Okay, very, very quickly, software or hand. There are a lot of little programs out there on the internet. Stay away from them. As a general rule, we've got no idea whether they work or not, okay? Anyone can write. Remember, the internet is not really peer-reviewed, okay? By the way, as long as they give you the calculation and the formula, I guess so, but that's fine. We do have specialized software packages like Pass, which are quite good. They're actually quite good, but just take care, okay? The problem I actually have with them is sample size calculations made easy. Not understanding the formula, plugging some values into software makes figures rubbery, okay? So people will change their minimal clinical difference. Do you think minimal clinical difference is something you can change? No. Something scientifically important or it's not. But if it's very easy to calculate things just by changing numbers, people will change those numbers around until they get the number they want. In other words, they make reality fit feasibility, not feasibility fit reality. Okay, so just be very, very careful. So think of it as a garbage in, garbage out type of issue. Okay, so there are a couple of sample size calculations I didn't cover. I didn't cover survival analysis, which has a couple of tricky things to it. And I'll probably cover that when I do cover survival analysis. Is survival analysis one of them, Alison? Yeah, okay. Okay, which I don't actually have sample size in that lecture yet. I'll have to put it in. I didn't talk about equivalence and non-inferiority trials, but by the way, there is quite simple adaptation to the formulas that I did give you, okay? Crossover trials, which I love talking about them, the only problem is hardly anyone uses them. I mean, many people do not work in areas where a treatment can be washed out, okay? A treatment has a lasting effect, a chronic effect, you could say. Multi-class outcomes, again, quite rare, okay? Diagnostic test evaluations, so sensitivity, specificity, yada, 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 that sort of thing, they are much more common, but because I've got a whole lecture on diagnostic test evaluations, I'm actually going to talk about sample size when I get to it. That is also generally not a power issue, it is a precision issue, even though we can compare diagnostic tests, which is power. So many of these aren't hard to do, they're just detailed and highly specific and quite rare. I mean, for a multi-class outcome, I think I've probably done about 4 or 5 in my career, sample size calculations for them, I mean. Okay, so just concluding, today we've covered formal sample size calculations used for the 2-group case for both continuous and binary endpoints. Fortunately, many analyses can be simplified down so these rules work. We've also adapted them to things like multi-class trials or cluster randomized trials. We talked about other covariates and adjusting for nuisance parameters. I also talked about informal methods that are better suited to exploratory observational studies. You could also consider simulation, but bear in mind you're probably going to need a biostatistician to work on that for 2 or 3 full days. There's a lot of programming involved in it and stuff like that. So you want one as a CI on your grant if you're going to do that, okay? There are many more sample size situations, but really the ones I've given you probably cover about 75% of the cases I get. I don't know about you, Alison.
Yeah, except I'm just trying to get the question simplified enough so that...
Yeah, that's right. It's a little dance. It's a dance, that's right. Particularly that MCD, the minimal clinical difference, no one wants to give you an answer. It's a confidence thing. Because say, oh, well, if I say this, what about if someone disagrees? And that's the sort of dance that I'll do. Okay, so the take-home message here is generally speaking, unless you're doing something very simple, don't do this at home by yourself. I would really come and see us for most sample size calculations, unless you're doing something very, very simple. All right, so we'll always help you with this. Really what I wanted to get across here is what are the important ingredients, the determinants of sample size. So just also get us involved very early too, in the proposal workup stage, okay? In the design things, because often what we'll say may change, you may change your mind about your whole design, okay? Okay, so thank you for that. Basically, I have just added a couple of other things here, and I'll make sure that these notes are actually available to you. Specifically, I talked about our binary outcome, but if we want to power it for a particular odds ratio rather than a difference in proportions, it's really very simple to actually adjust it. And I also did give you precision of prevalence, which is something I will actually cover in much more detail when it comes to sensitivity and specificity for diagnostic test evaluation. So again, I didn't cover it in the lecture. Again, good news is very simple calculations to do. Okay, that's that. Sorry, I've run out of time. Okay, any questions? That means I did a terribly good job or a terribly bad job if there's no questions. Okay, right, low blood sugar. See, that's why I talked about diabetes through there. Casey, basically, are we going to be able to give people these lecture notes if they want them? Yeah, because really I did design them in a reference manual type of way and to read through slowly. I know that this stuff is bouncing off your head. I don't understand it. So, okay, no questions? Has anybody got a grant application that's in the works at the moment? Good. That means we get to run away now. Okay, great. Thank you. Are there people waiting outside? Are there people? Oh. Okay.
If you do think questions later,
Yeah.
it's your contact details going to be on the notes as well?
Yeah, they're basically on the front page. Okay?
Excellent.
No problems at all.